Welcome to the Ontario High School video podcast series continuing with equilibrium, and we're going to look at what happens when you add a stress to the equilibrium system, and that's going to be described by something called Chatellier's principle. So this is part one, and stay tuned. Let's talk about what I would call a stark definition. If a chemical system at equilibrium experiences a change in concentration, temperature, volume, or partial pressure, then the equilibrium shifts to counteract the imposed change and a new equilibrium is established. This is from Wikipedia, the free encyclopedia, but this is as good a definition in its basic raw form as you'll find, and something you want to embrace throughout. Chatellier's principle can be used to predict what will happen to the amounts of reactants and products when an equilibrium system undergoes a stress. Stress is just change. The value of K remains constant unless the temperature changes. That is critical to remember. The value of K, once the shift has taken place, will remain the same unless the temperature changes. So, one more time, the value of K remains constant unless the temperature changes. If the temperature changes, the value of K will also change. Let's restate what we just talked about, and because I want the language here to be very precise, I'm going to quote from the Chemistry 7th edition textbook by Stephen S. and Susan A. Zumdahl. And this is a very authoritative chemistry text that many of you will run into at the university level. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. Let's look at the effect based on a change in concentration. We're going to examine a very common equilibrium system that you'll study called the Haber process, and the value for this is of K at this temperature is 6 times 10 to the negative second. Now, we're studying the addition of hydrogen to nitrogen to form ammonia, and you can see here we've written the equation as a thermochemical equation. So we have N2 plus 3H2 yields 2NH3. The double arrow represents this as an equilibrium system, and then plus 92 kilojoules. What that means is this is an exothermic reaction in which 92 kilojoules of heat is produced in this reaction. Now, we write the equilibrium equation, or the representation of the equilibrium constant, which is K is equal to the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. Let's again look at an application statement in as precise a way as possible, quoting again from Chemistry 7th edition by Stephen S. and Susan A. Zumdahl. If a component, a reactant or product, is added to a reaction system at equilibrium, this is at constant temperature and pressure, or constant temperature and volume, the equilibrium position will shift in a direction that lowers the concentration of that component. If a component is removed, the opposite effect occurs. So let's take a look again at our equilibrium system and consider if we add nitrogen, N2, to the system, how will the concentrations of the reactants and products be affected? So let's take a look at how this will be affected. If we add nitrogen, essentially we're increasing the amount of nitrogen available to react. From our application statement before, we said that if we add a reactant to a system at equilibrium, the equilibrium position will shift in a direction that lowers the concentration of that component. In this case, the reaction would shift to the right in order to lower the amount of nitrogen that's there. So we would decrease the hydrogen amount because the hydrogen would be reacting with the nitrogen to form ammonia, and the amount of ammonia would increase. Adding reactant would cause a rightward shift to favor the formation of more product. Let's look at another equilibrium system. Here we're adding heat to solid calcium carbonate, and we're decomposing it to form calcium oxide and carbon dioxide gas. When we write our equilibrium constant expression, we do not include solids for reasons that we've discussed in previous podcasts. Changing the amount of a solid does not affect the equilibrium system. So our K would be equal to the concentration of CO2, or if we do this as equilibrium pressure constant, K sub P would be equal to the partial pressure of the carbon dioxide. So our question is, how will the amount of carbon dioxide be affected by the addition of calcium carbonate solid? And you're probably thinking, you just said that it doesn't affect it. And you'd be right, but you have to be able to answer that question. So here we are, considering this system. How will the amount of CO2 be affected by the addition of calcium carbonate? It will not be. Adding a solid does not affect the amount of carbon dioxide gas in this system. Alright, another sample problem. We're looking at the Haber process again, reacting nitrogen with hydrogen to form ammonia, which is NH3. If we remove ammonia, NH3, if we remove that from the system, how are the concentrations of the reactants affected? What I'd like you to do is go ahead and just pause the podcast and answer that, and then come back and we'll see how you did. Okay, welcome back. Let's check your answer. If ammonia, NH3, is removed from the system, how are the concentrations of the reactants affected? Well, the equilibrium will shift to the side of the removal, meaning it's going to shift right, and more product will be formed. So nitrogen and hydrogen will both decrease as more ammonia is formed to replace the ammonia that's being removed. So hopefully you did well on that. We have another problem for you to try, and here it is. Okay, let's do a your turn problem here. Consider the following reaction that reaches equilibrium at 520 Kelvin. We have hydrogen gas reacting with iodine gas to form hydrogen iodide. And heat, so you can see this is an exothermic reaction. What will happen to the other reactants and products if A, hydrogen iodide is removed, B, hydrogen iodide is added, C, hydrogen is added, and D, iodine is removed? State as well whether the equilibrium shifts left, right, or is unchanged. So if you go ahead and pause the podcast and do that, we'll come back and see how you did. Okay, let's check your work. If we remove hydrogen iodide, it's going to shift the equilibrium to the right, to the product side, and both hydrogen and iodine are going to decrease. If we add hydrogen iodide, the reaction will shift to the left so that more reactants are formed, so H2 and I2 are increased. For part C, if we add hydrogen, the reaction will shift to the right and iodine will increase. It'll be used up as more hydrogen iodide is formed, so hydrogen iodide increases. And then finally, if iodine is removed, the reaction will shift to the left, your hydrogen will increase, and hydrogen iodide that is decomposing so that more iodine can be formed, that would decrease. So hopefully you did well on that. If not, go back, rewatch the podcast, and work through this again. Well, we've come to the end of part 1 of the video podcast series dealing with Le Chatelier's principle, what happens when an equilibrium system is stressed. We'd like to leave you with a quote from the wonderful actress Emma Thompson. It's unfortunate, and I really wish I wouldn't have to say this, but I really like human beings who have suffered. They're kinder. I wish you well. Stay tuned for part 2.